Hello kids, we are looking at section 17.2. It got hole punched out on polar area. And it's kind of a lot like what you do with normal integrals and areas, except instead of the shape being rectangles that you divide it into and how many infinite number of rectangles can you have, this is now like a sector of a circle, which is like a piece of pizza. So there's an infinite number of sectors that we use to find the area, and remember that a sector is a hunk of a circle, or like a slice of a pizza. And so here's what the area formula is. It is 1/2 theta times pi times r squared. There is no pi involved. It's just 1/2 theta r squared. Theta is in radians. It has to be in radians. And the area is bounded by the lines of theta being alpha and beta. So the bounds are alpha and beta. Here's the big old formula right here for you. So if we want to find polar area, that's the go-to formula for this guy. All right, find the area bounded by the graph of 2 plus 2 sine of theta. Now, if you want to graph it, we're going to graph some of these, maybe not all of them. It kind of looks like this. And so what you're looking at is this area in between. The area in here. How do I know what that looks like? Because back in 17.1 I graphed all these things. And I have a calculator that can do it. All right, so there's the picture. One of the facts that I remember about this particular function, and we made note of this back in section 17.1, is that to make a complete graph for this, how much did it take? That's going to be important to us. For this particular function, since we've seen this guy before, the complete graph had 2 pi. It took 2 pi to make this thing. And so I want to find the area of that shaded region. My area is, from my formula, 1/2 the integral. And the bounds are made up for how much it takes to, in this case it is the complete function that I'm looking at. Sometimes it's only part of the function, but in this case it's the complete function that goes from 0 to 2 pi, because that's how much it takes to make that complete function, of r squared. Well, r is right here. R is 2 plus 2 sine of theta. Okay, 2 plus 2 sine of theta, quantity squared, r squared, with respect to theta. Theta is like my x. And so I go to my handy-dandy calculator, and I put it in the calculator, and out pops 18.850. That's what the area would be. So it's just a matter of using a new formula. I mean, obviously it's going to get a little more fancy pants as we go along, but that's the general gist. So the second one, example 2, says, all right, find the area of 1 petal. Well, here's what this guy looks like if I were to graph him. He's very flowery. That's what he generally looks like. I mean, you only need a rough sketch. You don't even need a sketch, technically. But the deal is they only want 1 petal. Well, 1 petal is only one of these things. So I only want 1 petal of this. Sometimes they'll say 2 petals. Sometimes they say the whole thing. And again, I go back to what I learned in section 17.1 about these. To graph this complete function, it only takes pi. So my complete graph now is from 0 to pi. Why is that important? It's important because it gives you the bounds, if you can remember it. So let's put the area formula together. Now I'm going to leave a little space. We'll talk about the space in a minute. It's going to be 1/2 the integral from 0 to pi, my bounds, of r 2 sine of 3 theta squared d theta. Now the only thing is, that will give me the graph, or the area for the entire thing, right? I don't want the entire thing. I want 1 petal. So how do I adjust that in the formula so that I only get the 1 petal? I only want 1/3 of the area. I want the area for 1 part of those 3. And so that's going to be my setup. And so I put that together and I put it in the calculator again. it gives me an area of 1.047. If you're having trouble putting these in the calculator, give me a shout out in class and I can help you with that. All right, example 1, example 2, example 3. Find the area of one petal for this guy. Well, what does he look like? Again, if I were to graph it, I can graph it in my calculator. Some of these are ones that you saw back in the last section. This guy has 4 petals lying on each of the axes. They're all the same size. I mean, I know my picture doesn't do that justice, but you get the idea. I want one petal. One petal. Let's set up the area. I'm going to leave a space. It is 1/2 the integral. Do we remember how much it takes for this guy to make a complete graph? And if I go back and look, it takes from 0 to 2 pi for him. That's my bounds. 0 to 2 pi. My r is cosine of 2 theta squared d theta. But I don't want the entire graph. I only want one petal out of 4. So I want 1/4 times 1/2 times my integral. And again, put it in the calculator, I get 0.393. All right, here's where example 4, where they change it up. So can it always be that easy? You know how math grows. It's not the case. So here's what the next one looks like. They want one loop of this being r squared. Well, that's r squared. All of my calculations are based off of r. So I need a square root to go with that. And that's going to be the square root of 4 cosine of 2 theta. All right. So if I try the same thing I've been doing with this, I'm going to end up with an answer of 0, which isn't the case. You know you can't have a 0 area for something that's physical like that. It looks like an infinity sign. Okay. So when I was doing these examples, I started doing this one exactly the same way I did the others. Honky-dory happy, and realized that I got an answer of 0 for an area that can't be possible. So I had to approach it from a different route. And so here's the story. I have to figure out where this equals 0, where the pole is for this thing. And the way that I do that is I take r and set it equal to 0, because remember the pole's at 0. So if I do that, I'll have 0 equals the square root of 4 cosine of 2 theta. And my job is to solve for theta. Okay, so let's see if we can do that. Square both sides, I still have 0, equals 4 cosine of 2 theta. Divide by 4, I get 0 equals 2 cosine of 2 theta. Actually, 0 equals cosine of theta, 2 theta. The 4 divides out. So then the question for me is, when does the cosine of theta equal 0? Cosine of theta equals 0. Usually it doesn't really say. Usually it's going to happen in 2 locations. Cosine of 0 of theta equals 0 at pi over 2. Right? So if I go up the unit circle at 90 degrees, pi over 2, I get an x coordinate that's 0. So that's what I'm talking about. So theta equals pi over 2. And look at the other way that this thing, it also equals it at 3 pi over 2. But what's another name for 3 pi over 2? If I went in a negative direction, it'd be negative pi over 2. I'll explain why I need those and not 3 pi over 2 about this in just a second. Okay, so what then does that mean that 2 theta, remember my angle's 2 theta, what would 2 theta then be equal to? Well, that means I would have to get 2 theta, I would end up having to divide by 2, so this is really a pi over 4. And this would be a negative pi over 4. Well, I guess I should put this the other way. Negative pi over 4. I want 2 theta. Let me change my 2's. I know I have 2 theta, and the place where it equals 0 is pi over 2. This one, the place where it equals 0, is negative pi over 2, so that when I divide by 2, I get pi over 4 and negative pi over 4. They're ultimately what my angles are. And so here's kind of the idea with these. If I were to use this and think about the unit circle, coming from 0 going this way, right, that's where my theta is, this would be about at pi over 4, right, if I were to take that and put that value there. And if I'm over here in the 4th quadrant, because I'm in the 4th quadrant, I'm not looking at 3 pi over 2, I'm looking, or 3 pi over, actually, if this one, if it were negative pi over 4, it'd be 7 pi over 4. I'm not looking for 7 pi over 4, I'm looking at negative pi over 4. So those two tangent lines, because of where they're located quadrant-wise, is why I'm using the values I'm using. I think it might work the same if you were doing... no, it wouldn't, because if you went through 7 pi over 4, it would take in that other loop. All right, so let's set up the area. Area equals 1/2. And this time I don't need the extra little 1/4 that I did here. I don't need the extra 1/2, because this time I'm only going from negative pi over 4 to pi over 4. I'm only taking this section in right here. So I don't have to half it or do any of those 1/3, 1/4 that we did previously. It's straight up the formula. Going from negative pi over 4 to pi over 4 of my r, which is the square root of 4 cosine of 2 theta squared d theta. Now, for putting this in your calculator, you know if you square the square root, it gets rid of it. So you can just put in 4 cosine of 2 theta going between negative pi over 4 and pi over 4, and then take half of that. And it turns out to be that is 1/2 times 4, or a value of 2. So there's one that's a little bit more dicey because of the way that one didn't fit the bill of like the functions that we learned back in 17.1. So I didn't know exactly how much it takes to complete that graph. All right, so let's try example 5. This guy is find the area inside of 3 sine of theta and outside of 2 minus sine of theta. I have no idea what that guy looks like. So here, let me graph it. You're going to go to your handy dandy calculator and do that. You get a circle like this for the r equals the 3 sine of theta. Remember, they are circles and they lie on, sine guys lie on the y-axis. With this guy's a radius of 3. The bottom guy, this 2 minus sine of theta, he's kind of like, he goes flat, but then he goes circular, and then he goes flat again over here. And again, we did pictures like this back in 17.1. But here's the part you're looking for. You're looking for this part. The part that is inside of r equaling 3 sine of theta. Right? And outside of 2 minus the sine of theta. So this is the part that I'm looking at right in there. This guy is my r equaling 2 minus the sine of theta. And here's what I need to do. I need to find these points of intersection because they're going to be my bounds. And so how do you do that? Just like you would do it if it were a regular function. If I want to know where they intersect, I set them equal to one another. So I get 3 sine of theta equals r minus the sine of theta. If I have, now just think algebraically, if I have 3 sines here and I add one more over, I get 4 sines equals r equals, actually equals, I said r, it's really a 2, isn't it? A 2 minus the sine of theta. So that means that when I move that sign over, he's left with a 2. If I want to know what the sine equals, I divide by 4. So I've got the sine of theta equals 2 over 4, which is 1/2. So I go around the unit circle. Where is the y value? 1/2. And so if I think about it, it's going to be at pi over 6 and 5 pi over 6. First quadrant, second quadrant. First quadrant, second quadrant. Cool. So if I think about where these guys would be, I'm looking at this guy being pi over 6. Do you need to label this? Absolutely not. I'm just showing you for kicks and giggles. This guy's 5 pi over 6. Okay. Now I've got my bounds, so that's going to help me, but this one's going to be a little bit different, and there's several different approaches that you can take. I'm going to take you on the one that I think is easiest to see, and that is that you've got a full circle right here. Regular old circle. If I can take that circle and subtract away this piece, now remember I'm only looking between pi over 6 and 5 pi over 6. If I can take the circle and subtract away the 2 minus the sine guy, that's going to give me what my area is for this. It's almost like back in the day of finding area for regular functions with with calculus, where you're taking the top minus the bottom. Remember those rectangles, the representative rectangles and such? Same idea. All right, so my area is 1/2 the integral of pi over 6 to 5 pi over 6. And then I have the outermost, the top of the thing hits the 3 sine of theta squared, and the bottom hits 2 minus the sine of theta squared d theta. So it's a lot like top minus bottom from back in the day, that with that representative rectangle. All right, again, toss all that in your calculator, and the area comes out to be 5.196. If you're having trouble in the calculator, again, let me know in class and I can help you out. All right, here comes the next one, example 6. Example 6, find the area of the inner loop of the graph of r equals 1 plus 2 cosine of theta. What does this guy look like? Well, he's one of those that has a little loop-de-loop in the middle. He looks like this. And so the question's saying, find the area of the inner loop. That's this guy. I want to know where where this thing equals 0, where the pole is 0, right here, right? I don't need points of intersection like I did back in example 5. This guy I need to know where it equals 0. So I'm going to take my r, take my function, 1 plus 2 cosine of theta, and set it equal to 0 to figure out when it touches the pole. All right, so 1 comes over, 2 cosine of theta is -1, cosine of theta is a -1/2. You'll see a lot of repeats in these values as we go through them. Now let's think about these. There's a couple places where this guy equals a -1/2. It's where your x value would be a -1/2, and that would be at 2 pi over 3 and at 4 pi over 3. Now think about that with my intersections for this thing. One would be going this way in the second quadrant. This guy is my 2 pi over 3. And the other one, if I intersect this going this way, tangent it, it's 4 pi over 3. So it kind of makes sense that it's in the second and third quadrants. Kind of verify that. And then I'm ready to set up the area again. 1/2. My bounds are 2 pi over 3 to 4 pi over 3. And my r is 1 plus 2 cosine of theta, quantity squared, d theta. Again, go to your handy-dandy calculator, and it gives you an area that is 0.544. So a lot of similarities to things that you know from Calc AB with finding areas and such. Examples 7 and 8, because we are a bit on the time frame, they get a little more complicated, so we are going to skip 7 and 8, and I'll tell you about homework problems you can skip as well when we get there. But I do want to look at number 9. This is our last example, but of course it's got 4 parts to it. So, this one can actually be done without even looking at what the graph looks like, but just for fun I can show you. It kind of comes out looking kind of funky. It's very wonky. It goes like this, comes from this origin, kind of goes like this, and then comes down and lies on the x-axis. It's a little smoother, not quite as pointy as I have it over there, but you get the kind of general idea of it. So, number 1 says, find the area bounded by the curve and the x-axis. And so you say, I know how to do area. And they gave you your bounds, so you don't even have to find them this time, which is sweet. All right, so my area is 1/2 the integral going from 0 to pi. What's r? R is theta plus the sine of 2 theta squared d theta. All right, there it is. Put it in the calculator and you say 4.382. Thank you very much. All right, now this brings in some of the stuff that we learned from previous sections. So part B says, find the angle theta that corresponds to the point on the curve where x equals -2. Well, if x equals -2, do you remember that x equals the cosine? I mean, actually, it equals r cosine of theta. X equals r cosine of theta. If you remember that fact, then we can say that r cosine of theta, I'm going to multiply r cosine of theta, x, equals this. All I'm doing is multiplying both sides by cosine. So r times cosine of theta, this times cosine of theta. Remember, you got to keep the balance. So I'm taking, there goes Levi, theta plus the sine of 2 theta, and then I'm timesing that by cosine of theta. Well, they're telling you what x is. This is what x is. So if this is x, then x is -2. I can replace that with -2 equals theta plus the sine of 2 theta times the cosine of theta. Can you distribute that through? Sure you can. Doesn't much matter how you do it, because now you're going to go to your calculator and you're going to solve it. Go to the calculator and solve that guy. And again, if you don't remember how to do the solve function on your calculator, let me know that too. Theta is 2.786. Okay, so that was just totally from the solve menu. And again, you want to check yourself and make sure that you get a value. If it gives you 2 choices, sometimes it does, make sure that you choose the one that's in your domain. So my domain is 0 to pi. Remember, pi is 3.14. I got 2.786. Cool, I'm in there. I'm in that domain. So if you have choices, you're eliminating based off of what the domain is. All right, this one says, okay, now see, for pi over 3 to 2 pi over 3, the derivative is negative. dr over dt. Derivative is negative. What does this say about the graph on this interval? Well, it means the same thing that it always does for any of our functions, right? If dr over d theta, is what they're calling it, is less than 0, in other words, it's negative, it means that r is decreasing. So if the derivative is negative, then the function's decreasing, right? That's nothing new. Again, from back in the day, we can, with AB calc, it means the same thing. It's the same type of deal. It's just you're talking polars. We can get a little more specific with this, and I can add in, or the graph is getting closer. To the pole, to that center, 0, 0 kind of thing, when pi over 3 is less than theta is less than 2 pi over 3. So in that range, because that's what they told me, that the r is decreasing or getting closer to the pole in that section. So the meanings are very similar, again, to what we learned back in AB. Here comes the last example. At what angle theta in the interval between 0 and pi over 2 is the curve farthest from the origin? Well, farthest from the origin is like a maximum. You're trying to find a maximum. How do you find a maximum? Well, you take the function and you take its derivative and set it equal to 0. Well, what's our function for us? It's r. So I want to know when r prime equals 0. So again, very similar to AB, the way that we're going to handle this. So here I go. My r is theta plus the sine of 2 theta, or x plus the sine of 2x, if that makes you happier, then convert it back. But just treat the theta as if it were an x. So I know that dr over dt, derivative of x is 1, derivative of theta is 1, derivative of sine is cosine of the same angle times the derivative of the angle. And then I'm going to take that and set it equal to 0. So 0 equals 1 plus 2 cosine of 2 theta. Swing things around and solve this out. 1 comes over, becomes negative, divided by 2. I get a negative 1/2 is what the cosine of 2 theta would be. Go to your unit circle. If I have where it's going to equal cosine would be a negative 1/2. 2 theta would equal that. It's going to be at 2 pi over, actually it's 2 pi over 3. Hold on. I think well, 2 pi over 3, that would be, yeah, then divide by 2. Yeah, okay, I'm freaking myself out over here and I didn't need to. 2 pi over 3 is your location for this guy, where it's going to be equal to a negative 1/2. And that's only because I'm only looking at values, and you'll see in a second, between 0 and pi over 2. So that's why I'm only taking 1 this time instead of 2. If I then solve for theta, I'm going to divide by 2 or multiply by 1/2. This was why I was looking at this. I was thinking that it wasn't going to reduce to what I wanted it to, but it does. Pi over 3. Pi over 3 is certainly in that domain between 0 and pi over 2. So is that necessarily where the max is? And this is something that we tend to forget. If they give me bounds, then I have to check the endpoints as well, because I don't know on this section that maybe one of these points might have a higher y value than this guy does. So I have to make a little table of values, and I think again you might remember this back from AB. Actually it's not x and y, it's theta and r, right? We have our functions, we're in polar world. Theta and r. Well, first theta I've got to check is the endpoint of 0, and then I want to check my pi over 3 that I found, and then I'm going to end with checking with pi over 2. And I want to know what that is in the r function. Well, the r function is this guy. So I'm putting this guy in my y1, and then I can go to the table and figure out these values here and see who's the tallest, who's the max. Well, 0 gives me 0, pi over 3 gives me 1.913, and pi over 2 gives me 1.571. So who is the max? And we say this guy right here, he's the max. He's the biggest y value. So he is the maximum at theta equaling pi over 3. So it's finding the max like you would normally find a max. Set the derivative equal to 0, solve it out. But then you also have to check endpoints if they give you endpoints. And so that's your story with this. All right, so what problems can you do? You can do all of page 1. You can do all of page 2. That's up to 12. And then you are skipping the next page. So you're skipping, sorry for all the flopping around. 13, 14, and 15, you're Xing those guys out. We are not doing those. But I do want you to do 15, all the parts. This is a good AP kind of question. So 15 is a yes, 16 is a no. Okay? Again, if you have any questions, shoot me an email or I will see you in class. And I did include on what I uploaded to our classroom page the answers to all of the things that we skipped. So if that you have the liking to try some of those questions too, you absolutely can. And I will see you again in class. Thanks for your hard work. We got one section to go. All right. See you soon.